This is Unit 7, Video 5. So here we're going to do a small problem relating to the heating curve that is a practical type of problem. So before we do that problem, let's talk about canteens. Now, canteen is a water jug that has been used for ages and ages, thousands of years, by wary travelers and soldiers and so forth. And what you do, it's essentially some sort of vessel that contains water for your journey, and you're going to go through the desert, or you're going to walk for a long while, so you need a container to hold the water in. Now, interesting, what they did is they actually covered this vessel, this canteen, with some sort of cloth or a leather. If you can just catch a rabbit, skin the rabbit, and take the necessary cloth, or from any animal, and you cover it. And then what you do is you actually dip it in water. So you come along the stream. There's a stream, and you dip this thing. You obviously take some of the stream and put some of the water in the canteen with all the bacteria in it. But what you do then is you dip the water, so this whole thing is wet. It's dripping with water, so just full of water. Now what happens as time passes is this water evaporates. As the water evaporates, it actually takes heat with it. Vaporization, remember, is an endothermic process, so heat is absorbed. Heat must be absorbed for it to evaporate. If this is made of metal, and metals are very good heat conductors, this especially helps, it actually cools the water on the inside. So if the water on the inside even started, as pretty cool water, we'll say 25 degrees Celsius, you can actually get that water down to a nice, cool, chilly 15 degrees Celsius just by using this process. What happens is, as the heat goes up, remember the heat of vaporization of water is about 41 kilojoules per mole, which, if you have a few moles of water, maybe a mole or two of water covering here, that's quite a bit of heat that can actually be absorbed away as this vaporizes. And as this vaporizes, heat is absorbed, and it absorbs the heat from the inside water, and water that's inside, cooling the water that is inside. So that's why a lot of these, in the olden days, are actually covered in some sort of cloth, some sort of material, to keep it wet, so you can actually cool your water and have a nice, refreshing taste before you go on and chop some more heads off in your next military journey. So nowadays, obviously, it's more for aesthetic purposes, just to look good. And nowadays, we have cold water, we have ice, everything. But this was a historical importance. So we're going to do a little calculation over this problem, and here is the calculation. How many grams of water can be cooled from 35 degrees Celsius down to 13 degrees Celsius by the evaporation of 45 grams of water? So we have a canteen type of situation set up, and we're going to get this is pretty warm water. You wouldn't want to drink this for a refreshment. I mean, this is kind of lukewarm water. If you want a nice refreshing taste, you want to get it down to 13 Celsius. That's nice and refreshing. And we have 45 grams of water that's on the outside of the canteen. So we'll say this 45 Celsius here's our canteen. This would be on the outside of the water. Now we're going to vaporize this. This is going to be vaporized. So we're going to calculate the heat of vaporization, use the heat of vaporization to calculate how much heat that would have taken off. And then we're going to apply this heat to cooling the water from 35 to 13. And so what we'll do is we'll use the two equations from the heating curve. Our heating curve, again, here's the heating curve. These are the four portions of the heating curve. Let's ask ourselves, which portions are we referring to on the heating curve? Well, as we're vaporizing this water, we're referring to this portion of the heating curve, and then we're going to try to cool water from 35 to 15. That is going to be this portion of the cooling curve. Essentially, we're kind of going backwards, but the numbers work the same way. It doesn't really matter. Right, so let's go ahead and find out how much heat we're going to be able to absorb by boiling 45 grams of water. So let's do that. Even though evaporation and vaporization require the same amount of heat. Evaporation just happens at regular temperatures, vaporization at the boiling point. But the amount of heat of vaporization is about the same. It's not exactly the same, but to a good approximation, it's about the same. So we're going to use this equation first. Remember, heat of vaporization equation has heat equals moles times heat of vaporization. So in our case, 45 grams of water has to be converted to moles. So we got 45 grams. let's go ahead and we got 1802 grams in a mole of water. So how many moles of water do we have there? Looks like it's going to be almost 3. So we got 45 divided by 1802. Actually 2.5, 2.49, so 2.50 moles of water. Looks like that's how many moles of water we have. All right, well, let's go ahead and put that down. 2.50 moles. Our heat of vaporization is at 40.79 kilojoules per mole. So what we get ourselves is a nice number of, we're going to multiply this out, 101.9 kilojoules. Now that's quite a bit of water, quite a bit of heat. So 102 roughly kilojoules is going to be absorbed away as this water evaporates. Now that will be absorbed away from the water inside. So we're actually going to apply it and remove the heat essentially from this portion. Technically we're using a cooling curve at this instance. So, but the numbers work the same way. But we're going to cool the water in here. Now, so this equation was the MCAT equation. Heat is MCAT. Now, if you take a look at the problem, it asks how much water, how many grams of water. So what we're going to be solving for here is actually the mass. We have delta T. We have this number that's from 35 to 13. We also have C, specific heat as a constant. And H in this case is going to be this number. This will be heat, because this is how much heat it took to vaporize the water. Now, because C, which is the specific heat of water, is 4.18 joules per gram degree Celsius, we'll actually have to convert this into joules. So this is actually 101,900 joules. Again, we just kind of went backwards. So this is 101,900 joules of heat. That's how much heat we have. So let's go ahead and put that in our equation to solve for our mass. You can do this before or after. Let me go ahead and rearrange the equation. Since I know I'm solving for mass, I'm going to divide the specific heat in the delta T to the other side, and I'll do heat divided by C times delta T equals my mass. Okay, so let's go ahead and put this in. My heat is 101,900 joules. My specific heat of water is 4.18 joules per gram degree Celsius. Again, that is just a constant. My delta T, my change in temperature, looks like I'm going up about 23 degrees Celsius. So 23 degrees Celsius would be my delta T. Now you'll notice that the degrees Celsius cancel out, the joules cancel out, and we're left with grams. Where is that grams? Right here. Joules per gram degree Celsius. So we are left with grams. Go ahead and put this in. And we got 101,900 divided by 4.18, and then also divided by 23. Make sure you plug this in correctly. So you get an answer that's 1,159.960. This is grams. So really, 1 kilogram. We have 2 sig figs as always. So 1.1 kilograms of water. Now that is pretty impressive. You can cool a whole kilo by 23 degrees Celsius if you vaporize water. This is a testament of the high heat of vaporization of water. Water has very, very strong intermolecular forces due to hydrogen bonding, so that hydrogen bonding allows you to really cool yourself. Now where this is practically applied is actually in sweating. Those of you that are humans will sweat. And the way our body cools us is exactly this method. What we do is we sweat, which creates liquid water, which then evaporates, which takes heat with it. And that heat is a pretty high number, and that heat cools the body by taking the heat away. So you're able to cool, and because you're about 70% water, you're essentially just walking water bags, walking canteens. You essentially, with the skin around you, right? So you essentially can be cooled this way very effectively. Alright, this wraps up the 5th video. We'll do some calculations in class.